This one labeled rung is the whole language of a PLC program. These are ladder logic diagram symbols, the shorthand every controls engineer reads on a ladder diagram. 2 vertical power rails on the sides, a horizontal rung across the middle, and a handful of little marks that decide when a machine turns on. Right now, it looks like a wall of brackets and parentheses. It is not. Every mark belongs to one of few families: contacts that read your inputs, coils that drive your outputs, and the timers and counters that add time and counting. Learn those families, and any ladder diagram suddenly reads like a sentence. So we will walk all of them, one symbol at a time, then wire a real start-stop motor rung so you can see them working together. Let us build the whole legend. Before a single symbol, the one rule that unlocks everything. A rung always reads left to right, like a line of text. On the far left is L1, the live rail. On the far right is L2, the return. Everything between them is one logical sentence. The symbols on the left are the conditions, the inputs you test. The symbol on the right is the action, the output you drive. And the rule is simple. If every condition on the rung is true, power flows all the way across, and the output on the right turns on. Break any condition, and the flow stops before it reaches the output. So the whole of ladder logic is this. If the inputs are true, energize the output. Keep that sentence in your head, and every symbol just fills in a blank. Family 1, contacts. These are your inputs, and they always sit on the left of the rung. A contact does one thing. It either passes power or it blocks it. The first is the normally open contact, 2 vertical bars drawn as a gap. In Allen Bradley terms, it is XIC, examine if closed. It is open until its input is on. Wire it to a start button, and pushing the button lets power through. So a normally open contact means continue the rung only if this input is true. The second is the normally closed contact, the same 2 bars with a diagonal slash through them. That is XIO, examine if open. It is the mirror image. It passes power until its input turns on, then it blocks. Wire it to a stop button, and the rung stays live until you press stop. So a normally closed contact means continue the rung only if this input is false. Open for on, close for off. Those 2 contacts express every input condition you will ever need. Family 2, coils. These are your outputs, and they always sit on the right up against the L2 rail. A coil is the thing the rung switches on. The plain output coil is a set of parentheses. That is OT, output energize. When power reaches it, the output turns on. When the rung breaks, it turns straight back off. It only follows the rung, no memory. Use it for a lamp, a valve, a plain motor output, then the pair that remembers. A latch coil has an L inside the parentheses, OTL, output latch. Energize it once, and the output stays on even after the rung goes false. And the unlatch coil has AU, OTU, output unlatch. That is the only thing that turns a latched output back off. Set and reset. The L holds it on, the U lets it go. Plain coil follows the rung. A latch pair remembers until you tell it to stop. Family 3, timers. A contact and a coil act instantly. A timer adds the one thing they cannot, a delay. A timer is drawn as a block on the rung, with a preset time and an accumulated time inside. The common one is the TON, timer on delay. When its rung goes true, it starts counting up. Once the accumulated time reaches the preset, say 5 seconds, its done bit turns on, and you use that bit to drive an output. So a TON means, wait this long after the input, then act. Its partner is the TOF, timer off delay. It does the opposite. It keeps its output on for a set time after the rung goes false. A run-on fan that stays on for a minute after you switch it off. On delay waits before it turns on. Off delay lingers before it turns off. Between them, that is every bit of timing a simple machine needs. Family 4, counters. Where a timer counts seconds, a counter counts events. A counter is also a block with a preset count and an accumulated count inside. The CDU is the count-up counter. Every time its rung goes from false to true, the count goes up by 1. Reach the preset, say 10 parts on a conveyor, and its done bit fires. So a CEU means, do something after this many pulses. The CED is the countdown counter. It starts at a number and steps down by 1 on each pulse, firing when it hits 0. And both are cleared by a reset instruction that drops the count straight back to 0. Count up to a target, or count down to 0. That is how a ladder keeps track of how many. Now, let us put the symbols to work on the rung every engineer builds first. A start-stop motor with a seal in. Read it left to right. First, a normally open start contact. Next to it, a normally closed stop contact. Then, on the right, the motor output coil. Press start. The open contact closes. Stop is already passing power, so the rung completes and the motor coil energizes. The motor runs, but let go of start, and that contact springs open again, so we add the seal in. Below the start contact, we branch a second normally open contact, and we drive it from the motor's own output. The moment the motor turns on, that contact closes and forms a parallel path around the start button. Now the rung stays live through the motor's own contact. That is the seal in or hold in. It latches the motor on with nothing but a contact and a coil. And stop? It is normally closed, so is passing power the whole time. Press it and it opens, the rung breaks, the coil drops out, the seal in contact springs open, and the motor stays off until someone presses start again. 3 symbols, 1 branch, start, stop, and seal in. That single rung is the backbone of nearly every motor control program. So where do you try this without a real PLC on the bench? Right here, in a free ladder simulator that runs in your browser. You lay down the rails, drop contacts and coils onto a rung, name your tags, and press run. Toggle a start input and watch the power flow light up the rung and energize the coil. Exactly the start-stop logic we just drew is the honest way to learn these symbols. Do not just watch, build one rung, force an input, and see for yourself when the output comes on. 10 minutes of that beats an hour of memorizing brackets. Here is the whole set on one page, your printable ladderlogic legend. Contacts on the left, normally open XIC, normally closed XIO, coils on the right. Output OT, latch OTL, unlatch OTU, timers in the middle, on delay TON, off delay TOF. And counters. Count up CDU, count down CDD. Screenshot this grid, pin it above your bench, and every ladder diagram becomes readable. Left side reads the inputs. Right side drives the outputs. Timers and counters add time, and counting in between. That is the entire alphabet. So here is the whole legend in one breath. A rung reads left to right. If the inputs are true, energize the output. Contacts are your inputs. Normally open passes power when its input is on, normally closed passes until its input comes on. Coils are your outputs. The plain coil follows the rung, and a latch and unlatch pair remembers on and off. Timers add delay. On delay waits, off delay lingers. Counters count events, up to a target or down to 0. And the start-stop seal-in ties it all together into the first rung you will ever build. Learn these ladder logic diagram symbols once, then go read a real program. Everything on screen was drawn and run in a free browser tool, a ladder simulator, and a searchable symbol chart, both free. Open Circuit Diagram Maker.app, build one rung, and start reading. The link is right below. Subscribe if this finally made ladder logic click, and I will see you in the next one.